Okay, so last time we talked about the very basic rational function, just 1 over x, and then its transformations. Today we're going to get a little bit more complicated than that, and we're going to look at some of the graphs of these rational functions. So again, probably a good idea to kind of define a lot of stuff that's going on here. First of all, a rational function, any rational function is a function that can be written in the form of f of x is equal to p of x over q of x. Now that's just a fancy way of saying you have a polynomial over another polynomial. Okay, it could be a linear over a quadratic, quadratic over a cubic over a linear. Okay, it's just a polynomial over a polynomial. Now most of the time for the domain, there aren't any restrictions. Okay, these are the values of x that we're allowed to put into the function. When there are no restrictions, we use this little double R thing here, and we say that it's all real numbers. However, with rational functions, we have to be careful because we are dividing here, and the Cookie Monster and Friends problem, you can't divide by 0. Okay, so therefore we have to be very careful. The domain is going to be all real numbers except when the denominator, that q of x polynomial, is equal to 0, okay, because then we would be dividing by 0 and that's not allowed. Two more definitions. A continuous graph, most of the graphs that we've talked about in Algebra 2 and up to this point are continuous. It's a graph with no jumps, breaks, or holes. Logically, a discontinuous graph then would be a graph with a jump, break, or hole. Okay, so let me talk about what those look like, okay? So, two discontinuity types. The first one is called a hole, and that is when the numerator and the denominator have the same factor. Okay, what does that look like? Well, you might have this little graph here doing whatever it does, okay, but it might be undefined at that value of x. Let's say that's like 3 or something like that. Okay, but if the numerator and the denominator have the same factor at that 3, then it's called a removable discontinuity, and it just creates a hole in the graph. It looks like a normal graph, but we're just undefined at that point. An asymptote, the vertical asymptote, I should say. That's when the denominator has a unique factor. Okay, that's what we saw in our parent graph. Okay, or something like it. This is where we have a vertical line where we don't cross. Okay, it's a type of discontinuity. Same with this hole. They're both discontinuities. Okay, I'll explain the difference with this in a little bit. So, sorry, couldn't find my next paper there for a second. Example 1, looking at the domain. What is the domain of the function? Well, as I mentioned before, the domain is just when the denominator can't equal 0. Okay, so we just focus on the denominator. Right now, if it's just asking about the domain, you ignore the numerator. So you would set the denominator equal to 0. And oh my gosh, it's a quadratic. It's a quadratic set equal to 0. You've got a number of different ways you can solve that. You could factor it. You could use the quadratic formula. You could complete the square. Thankfully for us, this one does factor. So you have x minus 3 and x minus 1. And then you set each one equal to 0. And x equals 3 and x equals 1. Okay, if you plug 3 or 1 into this function, you would be dividing by 0. You're not allowed to do that. So the domain of this function would be that x cannot equal 1 or 3. And for right now, there's a lot more complicated ways to write this, but for right now, that's all I want you to do. Okay. That means, looking ahead, there is going to be either a hole or an asymptote at 1 and 3. Okay, and I'll get to that later. Okay. Again, what is the domain of this function? You focus on the denominator, domain, denominator. Okay, all you do is set x minus 4 equal to 0. That's easy enough to solve. X equals 4. Again, if you put 4 into this function, you're going to be dividing by 0. Can't do that. So the domain of this function would be anything but 4. So x cannot equal 4 there. Okay, so that's domain. I don't want to call this the range necessarily because it's a little bit more complicated than that, but there are these things called horizontal asymptotes, okay? Obviously, if you have a graph, okay, a horizontal asymptote is just an asymptote that is written horizontally, right? If we had something like this as, again, our basic rational function, we have this horizontal asymptote at this value right there, okay? Now, there are three ways, three different cases with rational functions to determine what the horizontal asymptote is. And for all of them, you have to compare the degrees of the polynomials in the numerator and the denominator. So the degrees, remember, we go up here. The degrees come from the highest exponent of the variable. Okay, this was a degree 2. This is a degree 1. Okay, so you have to remember how to do that. So it's the highest exponent of the variable there. If the numerator has a higher degree than the denominator, then there is no horizontal asymptote. There's no HA. If the numerator is less than the denominator, if the degree of the numerator is less than the denominator, you have a horizontal asymptote at y equals 0, or the x-axis. And finally, if the degrees are the same, then you're going to have a horizontal asymptote at the line y equals a over b. Okay, so it's a horizontal line where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. Okay, I'll show you what that looks like in just a second. Okay, so finding horizontal asymptotes. All right, so again, you compare the degrees of the numerator and the denominator. Okay, this first one, the degree of the numerator is a 1. The exponent of the numerator is a 1. The degree of the denominator is a 1. So these degrees are the same, which if you look at that chart that we just filled out, that means it's going to be y equals a over b. Okay, now a was the leading coefficient of the numerator, the number in front of the highest degree term, so it's 2. B is the leading coefficient of the denominator. Okay, well, the number in front of the x here is just a 1. So you have a HA at the horizontal line y equals 2 over 1, or just y equals 2. When we put it all together, I'll show you what that looks like. Over here, the degree of the numerator is a 1. The degree of the denominator is a 2. Okay, so the higher degree is in the denominator, which just tells you that you have a HA at the line y equals 0. Okay. All right, let's put this all together. Let's see what this looks like. Find the domain, any holes or vertical asymptotes, and any horizontal asymptotes of the function, and then sketch a graph. Okay. Starting with the domain. Domain comes from the denominator. So you set x squared minus 1 equal to 0. Now don't just add 1 and then take the square root because you're missing something here. X squared minus 1, perfect square, x plus 1, x minus 1. So when you set it equal to 0, you get negative 1 and positive 1. Okay? That's what x actually can't equal. Okay, so there's your domain. That's step 1. Step 2. Are these holes or vertical asymptotes? Okay. So step 2, this part right here, compare the factors of the numerator and the denominator. All right, so after you factored x squared minus 1, this is what you have. If you have the same factor in the numerator and the denominator, essentially if you can cancel that out, like you can right there, that means that this factor is going to be a hole. And that means that this factor is going to be a vertical asymptote. All right, let me show you what that looks like. Okay, way over here, we were to graph that. All right. Now remember, you got to set them equal to 0. So at x equals -1, you have a vertical asymptote. Okay. And then at x equals +1, you're going to have a hole. Now I'm going to show you what that looks like here in just a second. Because before we can do that, we need to determine what our horizontal asymptotes are. Okay, so again, that comes from comparing the degrees. You have a degree 1 over a degree 2. As we saw up here, that means that we have a horizontal asymptote at y equals 0, or the x-axis. So along your x-axis, you have a horizontal asymptote. And now you just fill it in. And for the most part, if it's just like this, where you have one of each, it's going to be bottom left and top right. But again, remember, you have a hole at x equals 1. So at x equals +1, you just draw a little circle and then continue on your way. And that's what the graph of this function looks like. Okay? All right. Next one, x squared plus x minus 2 over x plus 2. Step 1, find the domain. Domain is the denominator. X plus 2, set it equal to 0. Well, that means that x equals -2, which is actually what our domain can't equal. Okay, so we know we're going to have either a hole or an asymptote at -2. Now to determine what that is, we we look at the factored form. So now we have to factor the numerator, x squared plus x minus 2. When we factor that, you get x plus 2, x minus 1 over x plus 2. All right, so you see the factor, it gets removed. Okay, it can cancel. So this is a hole. Now, looking at the rest of it, since we've canceled it off, we're just left with the function x minus 1. Okay, up here, we were left with the function 1 over x plus 1. We still had a rational function up here. That's why it still ends up like this. But here we just end up with x minus 1. Well, if you were to graph the equation, y equals x minus 1, what does it look like? It looks like a line. It's in slope-intercept form. It's got a slope of 1, a y-intercept of -1. So if you graph this, all you need to do is you're going to draw a line. Let's see. Y-intercept of -1, slope of +1. So it just is going to look like that. However, at x equals -2, okay, so about right down here, you have to insert a hole. Okay. But Mr. Samstead, what about the ha? Well, compare the degrees. 2 over 1, bigger degree in the numerator. So there isn't one. And that's what we see here. We don't even out, we don't level out to a specific number as we approach infinity or negative infinity. We just keep growing. Okay? When you remove everything from the denominator, you're not going to have a ha, it's going to look like a line. Okay? So that's what this graph is going to look like. Finally, the last one, starting with the domain. X minus 3 equals 0. Easy enough. X can't equal +3. Okay, so we know we're either going to have a hole or an asymptote at 3. Compare the degrees. That's step 2. That's not step 2. That's step 3. Look at the factors. You have 3x plus 1. That doesn't factor at all. You have x minus 3. That doesn't factor at all. So nothing cancels. So that tells you that this denominator is a vertical asymptote. Okay, so we know we're going to have a vertical asymptote at x equals +3. So we put that in right away. Okay, now before we just start graphing, okay, we got to figure out our horizontal asymptote. Degree of the numerator, is a 1. Degree of the denominator is also a 1. So they're the same. So it's the leading coefficient over the leading coefficient. 3 over 1, which is the line y equals 3. So you have a horizontal asymptote at y equals 3. And then again, when you just have this kind of like vertical and horizontal situation, much like up here, you're just going to fill it in bottom left and top right. Okay, and there's no more holes. There's nothing else. The only discontinuity we had was at 3. We already took care of that. So it's like that and like that, and that's it.